So hi everyone, I'm Pranav Deshpande and I'm from Indian Institute of Technology, Madras, India. So my paper reads simple fabrication process for high sensitive, flexible capacitive force sensor. So this is how my sensor looks, and so this is basically a force sensor, and just to get this. So the if you take the cross section from this side, this cross section will look like this, and if you apply force from the this direction, the electrodes, these are the electrodes which are interdigital. They will separate from each other, or they will move away from each other, and that's why the capacitance of this interdigital structure is going to change. And this is what this flexible capacitive sensing equation, which is very well known equation. So this D is very distance between this electrode is proportional to the capacitance. So this we wanted to incorporate in the soft robotics, human machine interface, and wearable devices, such as suppose there is one manipulator and we want to or a grasper, we want to grasp some object, so we can easily incorporate this flexible sensor into any kind of shape, and we can measure the force. So this is what the basic idea is. So these are the contents I will talk about. I'll talk about some theoretical frameworks, how I model the interdigital structures, fabrication process, performance matrix, over results, and the key findings and our future work. So this is the theoretical framework. So we have basically came up with the two very simple model. First is a geometric capacitance model, and the next is a mechanical force model. So basically, in the geometrical capacitance model, we just know what is the initial capacitance of our sensor with using some set of equations. I will talk about those equations in the next slide. So this dimension, what is the width of the electrodes, the gap between the electrodes, and the dielectric of the material, which we will fed into the geometric capacitance model, which will give us different kinds of width and the gap. And this from this curves we can find out what capacitance range we want to operate in. So this will fed be into the force mechanical model, force versus capacitance, and this will give us the force versus capacitance. So now I will talk about this model in details. I'll not go in details with these equations. So this I referred from the one of the literature, and these are the capacitive sensors, and this can be easily found out using this elliptical integral of first kind, which is very known. And this is a simple mechanical model which takes into account Poisson's ratio, the Young's modulus of elasticity, and the force. So basically this D from this equation, which is the gap between the interdigits, we are going to change with using with force. So if we apply force, the capacitance is going to change accordingly. And these are some parameters which can affect the interdigital structure, where N is the number of fingers which we have, and so on. Okay. So this is about the fabrication process. So I fabricated this entire sensor using semiconductor manufacturing process. So which are more known for the rigid substrate, but since we want to fabricate for the flexible substrate, we took a silicon wafer, we deposited a PDMS on top of this, which is a very usual proportion, 10:1. Then we deposited chrome, gold in some, and we did a photolithography using some photoresist and etched the interdigits, and we removed the PR and using flood exposure. So one problem you will also face while reading the literature about PDMS, it is very bad with organic solvents such as acetone, IPA, and all. So we have completely avoided acetone, IPA, and those kind of chemicals, and we came up with this fabrication process. And after that, we connected the interconnected wires, which is enameled copper wire, and we will and after that I encapsulated this sensor in using PDMS itself. And after that, after every final process, I separated this flexible sensor from the rigid silicon wafer. So this is how the flexible this is how the fabrication plan works. And these are the after fabrication. These are the performance matrix which I calculated. So for every force sensor, these are the usual characteristics you will see: force range, linearity, and relaxation time, and so on. As far as this work concerned, we have only found out these parameters, and these are our future work. So this is how our experimental setup looks. This is one force gauge with push-pull stand. We will apply force from this direction, with using this lever, and the flexible force sensor, which can be read into from the LCR meter, and how much force we are applying, that we can see using this force gauge display. So this is how we have. So these are some results: force versus change in the capacitance. So if you increase force, as I told you in the first slide, there is one inverse relation between capacitance and force. So this fitted line is for the inverse relation of the capacitance, and this is how about the sensitivity and what values we can derive. That I will come back to that in the later slide. So this is the sensitivity change with respect to force. So in the low force regime, it is very high sensitive, and if we apply more force with that thickness, we can get the lesser thickness, lesser sensitivity. And this is about the dynamic response. We can apply one step input, and so this is basically a no load condition, and if you apply load, the capacitance gets reduced. And if you zoom this portion, you will get the time response, delay of achieving this final stage, which I found 60 milliseconds in both loading and unloading as well. So these are the key findings. Force range we have found out is 0.2 to 3.5 Newton, and the sensitivity is this highest sensitivity is 33.114% per Newton, and linearity, when you fit the model with the linear curve or linear regression, we will get easily the linearity, which is 81.34%, and these are the response time which I have got. So in the future, currently we are trying to experimentally found out the other parameters such as hysteresis, the drift over the period of time, the how sensor will work, and so on. And this is one more design we have proposed. This is a force sensor array. So this is not a one single sensor. So this will form a common ground, and pair of this one, this electrode, and this one will form a one sensor, and this like this it is a four number of sensors. So this will also act like kind of a Wheatstone bridge, so that you can apply force only in this this array, and these three will take account of environmental factors, and that will cancel out. So this is our future work, and these are some references, major references basically. And I would like to acknowledge Center for NEMS and Nanophotonics, and our institute IIT Madras, and the Ministry of Education. So that's about it. I'm very happy to take any questions.